So, what is called frequency domain filtering. So, all that we saw right now was actually in the spatial domain, right, and of course, you can actually, except for the right, a median filter which is nonlinear, the usual, if you had a convolution operation and all, right, we understand that one can do a frequency domain kind of filtering, and the way, right, in frequency domain you have to take and why frequency domain, it's very clear. Sometimes, right, it's easier to interpret things in the Fourier domain. For example, when I asked you how would you arrive at a high pass filter, right, you went to the all pass filtering, right, that's what occurred to you first, right, and then you sort of, right, mapped it back, it took its inverse, and then that will be a delta, and therefore, right, delta minus this. So you see that there is already another way to look at things which is easier to interpret, because, and similarly, right, that day when I asked you about log, right, if I just gave you the spatial domain thing, right, would you have been able to tell as to what might be its this one, when we said it's a band pass filter, definitely if I just gave you that expression, right, it will not be obvious to you that this whole, intuitively maybe yes, but then to get a real insight into why it should be a band pass filter would be possible only by going to a kind of a Fourier domain, right, where and there are various other reasons, right, why you want to go. So it could be like an alternative explanation or kind of interpretation, alternative interpretation, which is more, or an easier interpretation, or it could be that right, you have a computation, faster computation. Like for example, right, that a convolution, right, if you apply, if you do it in a Fourier domain, it's much faster, right, because you have the fast Fourier transform. Whereas in spatial domain, right, it's exactly the equivalent, but then you can do it much faster, so faster computations and so on. Okay, so there are a bunch of reasons why you can go to a Fourier domain, and it's completely one to one, right, it's completely sort of, right, invertible. So whatever interpretations you have in the Fourier domain, you can always come back and, right, and sort of interpret things in the in time domain or in the spatial domain. So there are, of course, frequency domain does not necessarily mean a DFT alone. Okay, there are other kinds of transforms and all. There's a whole class of transforms, what are called unitary transforms. DFT is one of them. And for a DFT, right, if I gave you an image f of mn, right, then this DFT is simple. So what you do is you write it as f of k comma l, and then you can do like mn going from, okay, right, depending upon the size, whatever, right, it's a finite size, some 0 to n minus 1 or something, and then you will have like f of m comma n, and then e raised to power minus j 2 pi by, okay, now let me write this. So the image size is like 0 to, let's say, n minus 1, and then 2 pi by n, then km plus nl, and where k and l also go from 0 to n minus 1. Okay. Now there is a lot of theory behind why this is so and so on, right, which we will not kind of talk about in this course. But the point is, in a straightforward way, right, this is what it is, and this is a straightforward extension of what you have for 1D, right. And sometimes, right, you might scale this by 1 by n square, right. It depends. Sometimes you have just a 1 by n there. There is a reason for that. Okay. I don't know what MATLAB implements. Does MATLAB do 1 by n square? Anirudh, what does it do? MATLAB uses it as 1 by n square or 1 by n. It's like unitary, or you get some. And this and again, at the same way that you interpret a 1D filter, right, you have like low frequency, then high frequencies and so on, right. A DFT, just in the same way, right, a 2D, right, a DFT is also somewhat similar, except that, right, you have to kind of remember that that when you take a kind of a DFT, right, and then let's say, right, this is some 1D signal f of k, and I gave you a sequence f of n, right, then when you reach n by 2, that's when you hit the highest frequency. Right, 0 is like the lowest frequency, n minus 1 is again heading to the lower frequency, in between is where you have the highest frequency, right. And therefore what happens is, in a 1D it's okay, but then when you plot it on a kind of 2D, right, then this interpretation becomes a little difficult, because we are typically accustomed to seeing the center at the center of the plane, and then we would like to believe that as you go out, right, you get higher and higher frequencies, right. Whereas if you directly plot f of k in this form using MATLAB or something, you don't get this feel. I mean, you see that, right? I mean, because of the fact that right, I mean, n by 2 is where, right, I mean, you will have the highest frequencies and so on. And therefore, what is normally done is there's something called frequency centering, okay, that people do. It's a very simple operation, just to swap such that, right, you get the low frequencies in the center, and then as you go out, right, you will get say higher and higher frequencies. It's actually simple, okay. I mean, just a matter of, it's a matter of, right, visualization, that's all. It has nothing to do with anything else, just a matter of visualizing. Do you want to visualize it like this, or for example, right, I mean, so it's like saying that right, I mean, if I wanted to especially in a kind of a 2D domain, it becomes more important than a 1D, right. I mean, you don't really bother so much. By the way, let me ask you just a quick question. Which is the fastest what do you call varying signal in 1D? Am I right? Huh? Which is the fastest varying signal? 1D, a discrete time, of course. Think about it, right? By the time, let me just see. Minus 1 power n, yeah, equivalently cos pi n, right? So I mean, so otherwise, right, you can have something that kind of goes and then changes, right? Whereas this is like alternate numbers like 1 minus 1 1 minus 1. I mean, you cannot have something faster than that, right? Okay, so the other thing, right, as I said, was this interpretation part, which we have already seen, right? So when we wanted to do that log filter, right, we saw, I mean, how to kind of get that expression. So I mean, if you go to a continuous domain, right, you saw that that gave you something like, so when you have log, so you saw that, right, this you have log, right, then you saw that, right, this gives out, so the Fourier, right, in a sort of a continuous domain looks like minus omega square plus nu square into e raised to power minus omega square plus nu square by 2 into sigma square. So right, this is a Gaussian with sigma, and then you are applying a Laplacian on that, right. This we saw is actually a band pass filter, and the interpretation became easy because we went to the Fourier domain, right. Otherwise this would not have been that easy. Now when you do a discrete, right, you have to be very careful. I mean, I hope you people have done that in 1D. So the omega, right, when you write it, I mean, you have to be careful. Okay, I am not going to talk about that. When you implement it, you will know that. If you have not done that before, you will realize that there is something that you have to take care of when you do a discrete equivalent of that. Okay, now right, based upon this, let me just show you a few more examples as to how how this what is this yeah, I mean, right, how these filtered examples, right, would look like. So let us just, right, quickly run through them. So for example, right, so what, okay, now the way right, the way to kind of write it is like this. You have an image f of m comma n, and then, right, you take a DFT of that, a 2D DFT, okay, which gives you f of k comma L, and then, right, this you modify with some mask. That's what you call that frequency domain mask, right. It could be whatever, filter you have, right. So we call this as some kind of a mask, and then out of this will come an f tilde KL, because this is simply a multiplication. So that mask could be a band pass filter, it could be a high pass filter, it could be a low pass filter, whatever it is, right. So you directly multiply in the Fourier domain, and then you do an IDFT, which is again 2D IDFT, and then out comes, and let us say f tilde m comma n, right, which is like a modified version of fmn, right. This is some filtered version, and if you try to see that here, right, in these slides, right, you will be able to. So here it is, right. So I was trying to show that here. Okay, so here you see, right. So if you see this, so in the Fourier domain, right, I mean, you have a filtering operation. Wait a minute, I think I'll show you the images, Gaussian. Okay, this is, so here, right. So what do you think should come as this image? If you see the filter on the right, filter shown in the frequency domain, right. So something like this is what is like a low pass filter. Therefore, what you should be getting is actually a blurred picture. Something like this is actually a band pass filter. Oops, what happened? Right, this is like a band pass, right. I mean, in the center you are blocking off some low frequencies, then outside the band you are again blocking off, in between you are allowing, right. So it's like a band pass. Therefore you see that, right, you get something like edges and then a combination, right. It's like it's like a band pass filtering operation. Then here, so what do you expect to see? This is what kind of, this is like a high pass filter, right, and therefore, right, you will get some edges. So again, all this, okay, if you low pass filter it, you should see a blurred picture, right, and if you did a high pass filter, then you should get something like, you see, edges. If you did a band pass filtering, right, you end up with something like that. Then this is another kind of band pass filter. So you can have, right, various examples where, oh, I think I've opened multiple number of them. Okay, so you can have different examples to get some insight about what is happening. Okay, now this thing, right, is actually this idea okay, has been also used in one, you know, is one is interesting kind of an application which I will talk about, which is called hybrid imaging. Okay, I'll just show you that's the picture, and then you can tell me what you can make of that. Okay, let me just go next. Okay, this noise, right, I've already told you, okay, how this works, this averaging and all, right. This is that salt pepper case. Okay, these slides are all there. Okay, so it's easy for you to just go through them. Let me just come to this. Okay, this is a median filter again. Okay, now there is something, right, something the way, right, the way, okay, we see things. I mean, something which is close by and something which is farther off. So if I showed you this image, right, what would you see, right? I mean, so you see a lady. I mean, are you able to see that? I mean, right, so out in the center, right, is there a lady, and this is actually an artistic picture by this guy. I think, what is his name? Salvador Dali, I believe. He is some Spanish artist or something, right? Now, what else do you see? You see that, I mean, you see that, right, there's a lady standing there, maybe looking out somewhere, but then there's something else, right, which you see in that image, right? What is it? Huh? You can see Abraham Lincoln, right, if you squint your eye. But actually, right, what you can do is, if you go a little farther off, right, and watch this, right, so if I just go farther off, now what do you see? Don't you see Abraham Lincoln, right? Now, right, this is something, right, because of the way we see things. So if you show something to me very closely, right, I'll see those fine details and all, and maybe I'll see something else. But then, right, when I go away, right, there is an averaging that goes on, right, as you go farther, as you draw farther and farther away, right, you kind of, your eyes tend to average things, and therefore when you average it, you see a kind of a low pass filtering effect. Okay, and hybrid imaging kind of takes use of these, makes use of both of these notions that we have, when we see things, right, depending upon how close or how far we are, and that's why it's called a hybrid imaging. So it sort of, makes use of things that are so it makes use of the idea that low pass filtering, right, typically has to do with being far away, and high pass is something like being close, and this sort of a dependence on a distance is what hybrid imaging exploits. And what it does is this. I mean, this is a simple idea. So what it does is this, right? So you have an image. I'll draw everything in 1D, right? But what you really do is, so you take a low pass filter, right? I mean, I am just drawing one side of it, one side of the frequency spectrum. So you pick some, say, sigma L, right? You pick some sigma L, right, for the say LPF operation. Okay, again, the sigma and all is under your control, and for image to image, all this can change. Okay, nobody knows what is the best value and all, but typically, right, you will choose a sigma L. That means, right, you give an image. Okay, this is the image on which you want to. So you have actually two images. Okay. I mean, right, these days people talk about style transfer and all, right. I mean, you can think of this as some a traditional way of trying to do some kind of a blending, right. So you have a low pass, so you send this guy, right. So let's say I1, right, you send it through this low pass filter, and the sigma L is up to you. Okay, and this other guy is actually, so if you do, right, 1 minus this, right, that will be in the Fourier domain, right, that will be some kind of an high pass filter. But then what you can do is you can pick either the same sigma L here, or you can pick something else. Okay, you can pick something like sigma H. Okay, some other sigma H, right. I mean, you can actually pick. I mean, and then what you do is, so for example, right, I mean, it doesn't have to be exactly sigma H does not have to be exactly equal to sigma L and all, but they say that it's okay even if you take that, it works reasonably well. And then what you do is you actually fuse the two. That's the hybrid part. So you simply pass this guy through I1, pass I1 through the HPF, pass I2 through the LPF I1, and then HPF I2, and then you simply add them in the spectral domain, and you take the inverse. And so it's all kind of, everything is actually linear operation. So the Fourier, everything goes through. And therefore, right, when you do that, okay, then I'll show you an example as to what effect, right, this can bring in, and this you can do for fun. In fact, I think we have I think we have some examples for you. Okay, that for you to try on, and okay, now see this, right. So there is an elephant, right, and if you low pass filter it, right, with some whatever sigma L, right, then you get the blurred elephant. And then you have actually a leopard, right, and that if you do some sigma H, right, with some high pass filter, right, you get get this image, right, in the middle, okay, what you have here. And then if you fuse them, that is this hybrid imaging, then what you see is this. Now, depending upon from where you watch this, right, it'll have a different appearance. Okay, if you go farther off, right, it will look like an elephant, but then it will look like a spotted elephant. Okay, whereas when you watch it from close, right, it will look like actually a leopard. Okay, and with some smear, right, in the front and back, which you can't take for a trunk. But if you go farther off, right, and see this, it will actually look like a spotted elephant. Okay, so I think this is called hybrid. These are all small tricks, right, that let's say people play, and and you kind of get some interesting kind of results. Then the other thing, right, that I wanted to talk about was actually sampling. Okay, just as in 1D, right, you can sample. Right, the next one that I wanted to talk about was sampling. And for us, right, sampling, I mean, right, you might ask why you want to sample and so on, but especially, right, a subsampling. So you want to go down from, you see, one size to another, right. So you want to go from a big size to a smaller size, and this you normally do because there is a computational reason for it. See, for example, right, I mean, people have shown that if you wanted to do some alignment of two images or something, right, then instead of directly working in the highest sort of a resolution that you have, you should actually go down, and then what you can do is, when you are down and then the sizes are very small, there it's easy to compute the alignment, and you get a good initial estimate to start with, and then you can kind of say build back. Okay, and this turns out to be more robust, turns out to be faster also. Okay, and because you have these initial estimates that are very good by the time you come to the highest resolution. Whereas if you start with a high resolution, you start with a very bad initial estimate, and then it takes much longer. Okay, so there are various reasons why you want to do this kind of a subsampling. That's called a pyramid structure. Okay, so what you will have is something like this, and then you go down. Then you go down. I mean, you can go down right up to a single pixel if you wish. Right. This is called this one, a pyramid. And in order to get, and this we will see. Okay, when we do the scale space representation, right, at the time we will see what is the implication of having a pyramid like this. But then, right, if you thought that I can just take this image at whatever size, let's say n by n cross n, and suppose I picked every alternate row and column value, then I'll reduce it to n by 2 by, say, n by 2, right. I mean, so the next guy will be like n by 2 by n by 2, and then the next guy will be like n by 4 by n by 4, and I can keep going down if I wanted to reduce by a factor of half, right, all the way, or by a factor of 2, right, if I wanted to reduce by a factor of 2. But then what typically happens is, if you try doing this, right, directly just like that, then you get actually what is called the aliasing effect. It should happen, right. In 1D, what will happen? I mean, if I did x of let's say, right, 3t, 2t, if I did, then what will happen in the Fourier domain? If I did x of 2n, right, I mean, instead of x of n, that means I'm dropping, right, every other sample. If I do that in the Fourier domain, what will happen? The spectrum, will it expand or will it shrink? It's running faster. It won't shrink, it will actually expand, right, and you'll have an aliasing effect, right. I mean, see, so for example, so what when it expands, right, you'll get the higher frequency, right, aliasing with the lower, right, that's what will happen. So a similar thing will happen, right, even with images. I mean, you have done that, right, in 1D, this subsampling and all you must have done, right. I mean, x of m by n in general, right, where you sort of which is also the reason why you first upsample and then you downsample, because if you first downsample, then right, I mean, all of that will get already mixed up. There is no point trying to interpolate and say upsample, right. So you first upsample so that you squeeze, and then you get to say downsample, right. So here, of course, there is no upsampling. We are talking about subsampling, which means that you are going down in terms of the size, and therefore, right, what you do is, so if you try to do that directly, right, this is what will happen. So therefore, what basically people do is they will always blur it. So which means that you limit the frequency, right, that this image has to some extent. So you may say, then am I not kind of losing because I am blurring, but it's okay. If you don't want aliasing, you actually limit the frequencies that it has, so that after that, if you subsample, you don't have this aliasing effect. And therefore, most of the scale pyramids that we see, right, you will have a blurring operation always. Okay, that is to simply limit the aliasing effect. So there are some figures, right, which might actually explain this better to you. So let me just go show that. Okay, so if you see, right, okay, so right, sampling. So I think I can probably, okay. So for example, if this guy, if you take, right, and then if this is too big and you start to downsample, right, this is how it will happen. If you simply take, take every alternate without actually blurring, and if you try to blow this guy back up to the original size, right, that's when you will see how bad, right, it's become. Okay, so it's like, you're like 1/8 the size, and then if you try to blow it back to the original size, you will see what all you've lost, and you can see that you lost, you lost a lot. Of course, you may not see the aliasing effect that well here. The aliasing effect, right, can come from here. See here. Right, don't you see that that is a picture, looks very quite far away from the other one, right, and these are actually aliasing effects, right, and then in images it can have a pretty damaging effect on the appearance, right. You might think that that's how it is. Actually, that's because of the way you subsampled it. And there is, I think, one more example also here that also illustrates this point. Now see something like this, a checkerboard. If you subsample directly, right, at the end, okay, you see that there's a lot of the aliasing, right, because those are kind of closely packed, right, and therefore the aliasing effects are higher there. And therefore, right, what you can do is, of course, you can say that well, maybe I should have a better sensor and all that, I should be sampling the scene at a higher rate and all that, but instead of that, people use what is called a pyramid, a Gaussian image sort of pyramid, where again the Gaussian, right, that we've been talking about all along, right, is actually used. So what you do is, so at whatever level you are, you first blur it with a Gaussian. Again, right, we will see later, what is, and this exact idea is also used to get a Laplacian of the Gaussian approximation, because you are anyway blurring with a Gaussian. So if you had two different Gaussians blurring an image, and if you were to take a difference, if you blur them the correct way and then take a difference, then you can get a log approximation, okay, and such things are done. But this kind of a pyramid thing right now, as far as we are concerned, it may be for various reasons, could be for computational reasons, or it may be a scale space representation, where you want to see structures in an image in a certain way, and which we will talk about, right, when we do SIFT and all feature detectors. And yeah, right. So basically, this is how it looks like, and blur, and then it's a subsample. So it's like always blur and then subsample, and then if you do this, right, then okay, then these are all like 1D examples, okay, and then, right, what you see is that the aliasing effects are actually much less. You can take some examples and show this. I am not so sure whether these examples bring that effect out, but then, right, that's really the point. Okay, no, actually, no. The idea is not like when you expand it, it won't happen. The idea is when you downsample it, the aliasing should not happen.
Yeah, by expanding.
Exactly. That's the idea. Not have aliasing. At the expense of losing some fine details. So now, right. So for example, right, in this case, I think, so now, right, yeah, this is an example. So when you blow it back, right, probably some people may like this better. Again, but then, but for this example, it doesn't seem to matter whether I had the phase the other way, where I did not blur and subsample, whereas here I blurred and subsample. But then, like the other, when I showed a tower, right there, it's going to matter a lot, because when you blow it back up, you'll get other patterns which are not there in the right original image itself. Okay, yeah, I think I'll stop here.